So we can move on to question 5. Question 5 reads, in a class of 100 students, each chose at least one of the 4 lunch options. All right, so they had choices of 4 lunch options: pizza, drumstick, meat pie, and hamburger. Okay, it was found that 65 students ate pizza, 80 at drumsticks, 80 again at meat pies, and 90 at hamburgers. All right, and there are 100 students altogether. What is the minimum number of students who ate all 4 options? All right, so you need to get the smallest number of people who ate the whole 4. Okay, let's just draw a Venn diagram so that we can understand this a little bit better. But you've got a Venn diagram of 4 sets. It's a little bit more complicated than the usual. So here's a Venn diagram of 4 sets, and we have okay, now I just want to see the people who ate all 4 are inside here. This is the X that I'm talking about, right? And we want to minimize X. You want to have a small number as X as possible. Okay. Let me just write down that pizza is 65 here, and drumsticks is 80. Meat pies is 90. Yeah, and hamburgers was 90. And meat pies is 80. All right, I just want to record that information in the diagram. Now we want to have this as small as possible, which means that the outside must be as large as possible. So you want, like, for instance, in this case here, you want as large as possible in the outside. Now, if you want this to be as large as possible, it means that the number of, now, see, the outside large as possible, this set, this part here, which is outside these 3, consists of people who ate only hamburgers, right? And they didn't eat any of the other 3. So this group here is the group which ate only 1. Right? And then here, these people ate 2 hamburgers because they, not 2 hamburgers, they ate, it's 2 items, 1 hamburger and 1 meat pie, and they didn't eat any of the other 2. Like that, you'll see that these are the 2 guys. I think this one here is also the 2. And then I'm calling the ones who ate 3 hamburgers are A, B, C, D here, right? Now that is what we want to maximize here. We want the others to eat as much hamburgers as possible so that you can minimize this. The number of 3 must be as large as possible. Okay. So how do you work that out? We know that they ate altogether, they ate 90 plus 2 80s plus 165 that is 315. Well, actually, when you say they, 100 students at 315 items altogether. And you want to maximize the A, B, C, D. So if each at each of the 100 at 3 items, then you have too much, right? You will get 400. So the best you can do is you can say 3 at each. If each at 3 items, then there are 100 of them, so there will be 300 items altogether eaten by the 100. Now, why we say 3? I just explained it because you want to maximize. I'm going to put a star there. Star says to minimize D, to minimize X, right? That's the four items. We have to maximize 3 items. And you can maximize it by saying all the 100 students at 3 items. So that will mean that they've eaten 300 altogether. But where did the other 15 come from? The 15 is, therefore, there are 15 students were at. So in addition to 300, you got 315. You got 15 extra. So where did that 15 come from? That means those 15 students at all 4 items. So X is actually equal to 15. Right? Now, so we know the answer is what is the minimum number? So that's the answer. But there's a huge challenge that is here, which might not be noticeable. This is the answer. But I'm going to put a question mark here because how do we know that we can actually group these? I can populate those with numbers so that you get 65 eating pizzas, 90 eating. What are these numbers? What's the value of A, B, C, D? Sometimes you might not get any solutions. No? You might not be able to find A, B, C, and D so we have to exhibit at least one solution. So we have to show that there is at least one solution. Let's say, better to say, find A, B, C, D. And to guarantee that there can be an X which is equal to 15. Okay, so let's see now. We have to use the mathematics for this. You've got, if you take the 65, that's the number of pizzas. Now I'm going to take out these 1, 2. These 1, 2 represent something else. They represent the number of pizzas that in those lots. Okay, so let's just remove that. Okay, so the 65 represents all the numbers in this group. So it is A plus B, A plus B plus C plus X. Oh, which is 15. We decided that this is going to be 15. The X is 15. Which means that A plus B plus C is 65 minus 15, which is 50. All right, so that takes care of the 65. Let's have a look at this 90 here. In 90, you will have C plus D plus A plus C plus D. A, no, 90. Yeah, it's A plus C plus D. That's in this lot here. Plus X is 90. So you have to take away 15 from 90. 15 from 90. And that'll give you 75. Okay, so this is 75. So what have I got so far? I got A plus B plus C is equal to 50. And I've got A plus C plus D equals 75. I just want to write all these under each other, so I need to solve these things. So A plus C plus D is 75. So likewise, now here D is removed, here B is removed. Let me remove A, that'll give me B plus C plus D. And so B plus C plus D is this one here. B plus C plus D the A plus B plus C is actually, this is 80 minus 15. This is not, this is 80 here. Because A, B, and C are here in the drumsticks area. All right. So you've got A plus B plus C is actually 65. It's 80 minus 15. Okay, now let me have a look at the B plus C plus D is in the 65 area. It's 65 minus 15 is 50. And then here I've removed D, here I've removed B, here I've removed A. And the only thing is left is remove C, A plus B plus D. And where is A plus B plus D? It's here, right, in the mid pies area. So that is 80 minus 15. And that is 65. So how do you got four unknowns, and you need to calculate them. And now you are not taught how to calculate four equations and four unknowns, but there's a very easy way of doing it if you check nicely. If you look at this, add all, right? When you add all, you get A plus A is 3A. The 3 A's and the 3 B's and the 3 C's and the 3 D's on the left-hand side. You can check that out. And when you add all here, you get 65, 140, 190, 255. That's what you get. So therefore, A plus B plus C plus D, because 3 times, if you divide by 3 right throughout, you see 255 divided by 3 is 85. So now that allows you to calculate. Now I know the sum of the 4, Like for instance, A plus B plus C plus D. Yeah, yeah. The four add up to 85. So D is missing here. So D is 20. D must be equal to 20. So what must you add to get 85? Here, what must I add to get 85? Must add 10, but the B is missing. So B is equal to 10. Here, what must I add to get 85? It's 35. The A is missing here. So A is 35. Let's make it like this, A, B, C, D. A is 35. B is 10. D is 20. The last equation, what must I add to get 65? I'll have to add 15. No, to get 85, I have to add 20. So this is also 20. So you got, if you put these numbers inside this, I got 35, 30, 35, 10, 20, 20. I try it out, and you will see that these numbers indeed add up to 65, 80, 90. This does give you a solution. And in that case, you will see that X will have to be 15. So this will be a solution. Okay. All right. Now, if you didn't follow that very carefully, let me just show you the actual answer, which I've written it in detail here. And there it is. You can see here 35, 35, 20, 20, 15. It's rather small, not easy to see, but okay. I thought I might make it a little bit bigger, but that gives you the answers. So, and these are the equations, and I haven't solved it fully, but in my discussion, I showed you how to do it. Okay, so let's get on to the next problem, which is question 6. Okay. Question 6 reads the following. There is an array of 10 switches, all in the off position. Okay. In every move, you must change the position of any of the 9 switches. In other words, from the off, you change it to on. Right. What is the minimum number of moves required for all 10 switches to be in the on position? So just to understand this, what it means is that I start off with the 10 in the off position. Let's give a symbol for off. I can put O for off and O for on, but that's terrible. Let's call it A for off. So your start, right, all in the off position, so it's all A. There are 10. 5, 6, 7, 8, 9, 10. And then the end, you let have all off. Right? Minimum number of moves required for all 10 switches to be on. So yeah, you got all B. So A is off and B is on. Now, in each change, in each position, you change the position of 9 switches. So let's look at the end. So you want to know what is the minimum number of moves required for all 10 switches to be in the on position. So you're starting off with A, all A's, and you make a first move. Let's call it move 1. And you move 9 of these switches. You keep one of them fixed. All right. So maybe I don't change maybe the last one, and then, so let's ring that to say we don't change that. So after one move, all these now become B. The 9 B's and 1 A. All right, now you want to know how many moves. This is the first move. You got the second move. Again, you fix one of them and you move the others, the 9, and you'll get some kind of a configuration, so on, until you come to let's make it, there will be n moves. The nth move will be something, but the final thing will be all B's here. Right. Now, if you want all B's here, it means that the previous one would have had all A's except one. So maybe we can say this one is A. Now all A's except one. Maybe this was B, and all these were A's. All right, the previous one would have to be like this. All right, now this becomes quite complicated, but what? Let's just take an example. Suppose we work with 4 A's instead of 10, and I don't move that. I put a ring around that which is not moved. So these switches are changed, and this is not. Okay. Now this is after the first move. Here it is. I've got a similar thing there. But now, just I can do this to anything. But suppose I fix that, leave that unchanged, and change all the others. So this becomes A, and this becomes B. All right, the third round, suppose I fix that one, A. Now this becomes B, and you got A. You can see we are at this stage here now. You see? One B and all A's. And then now, if I fix that one, they all become. So how many moves have you got? You got 1, 2, 3 moves. After the third move, you come to the starting point. So if there were 4, you can achieve. And wait a minute. This last one should have all B's. Sorry. Yeah, we're holding on to the B, and we move all the others. So this will be B. So now you come to all on. All right. So this is after 3 moves. So when you have 4, after 3 moves, you can come to all on. So it seems to me that conjecture with 4, you come to all on after 3 moves. With 10, we require 9 moves. But how do we prove that? That is a challenge. It's quite a challenge. And I'll try to explain as well as I can. So I'm going to assume, I'm going to say that there are 9 moves. But we want to show that this is a minimum, you see, the minimum number. So suppose there are n moves, as we had originally. I looked at 4 moves and realized, I mean, with 4 switches, I saw that there were 3 moves to bring it to the on position. So let's start off with N. Now I want to track any one of these positions, right? Suppose I track this one, A. Now A goes to B for the first round. And if B is not fixed, it goes to A the second round. And if A is not fixed, it goes to B third round. And somewhere along the line, if it is fixed, then it remains as B. But you have to fix it only once. And then after that, it becomes A and so on. And you want it to eventually come to B. Right? So you can see that to come to B, you got 1, 2, 3, 4. And one of them is fixed. After 4 moves, it comes to A changes to B. So after every 2 moves from this point onwards, it'll come to B. Yeah, it'll come back to B. So the the point is that in each of these columns, right, it's going from A to B, B to A to B. Right, it keeps switching off. But in one case, it remains still. Right? If it wasn't remaining still, then every time you take 2 moves, 1, 2, you come to A. Right? So an even number of moves will come back to A, but an odd number will come back to B. Right? But now one of these remains fixed. So you'll have an even number which comes to all A. To all A. Right? And now so this N here, the first time you come to the situation, each time you will have a new situation, and it would not be all B's because you keep changing until you come to this. So the least value of N is 10. Look, there's a lot of hand waving there, but the least value is 10. Because when you come to 10, then you have changed every one of these. You can't change any, you have to change a new one each time. So there are 10 altogether. So in the last one, in the 9th one, right? After the 9th move, you come to this, and we haven't changed this yet. The 10th move, you would have got all A's. And this is the 9th move, you'll get all A's, all B's. All right. So I get a little bit mixed up with the odd and the even. But anyway, if you think about that, you will see that the least value of N, you have to go through the whole lot. You have to move every one of them. Man, all have to be moved. No, they don't move. All have to be fixed at some move. And there are 10 of them. Right? So this last line here will be 10. Right? To get to all B's, therefore your N will be 9. There are 9 moves. Your last position will be 10, but there is no move from this point. There was a move. When I say move, I mean changing the 9, right, and keeping one fixed. Okay, so that takes care of this, and I actually got shown you how it's done in case you you are a little bit doubtful as to the authenticity of what I'm saying. Here you can see exactly. See, starting from all A's, you'll end up with B's, and you can see I am changing them one by one, one by one. The red means that I I don't move that, and I move all the others. So like here, I don't move this, so A remains the same, B remains the same, A remains the same, like that, right? Until you come to this position here, and B remains the same, and all the others are moved. But you can see that there are no line has got all B's in it. Right? The first time you reach it is when you come to A, because you have to move, you have to fix all 10 at some point or the other to get all B's. Otherwise, you don't get to that. Okay, that is the logic behind that. Okay, so that takes us to the next one, question 7. And these problems which we have done here so far, they are quite difficult. I found them very difficult, I have to say. Although I come here and make it look as if it's so simple, I can assure you that it took me a long time to solve these problems. Okay, or even to understand the solutions. In some cases, I had to check to see. All right, now the next question is, find the values of x that satisfy the equation root 1. I think you need to say integers. I don't know why they say this. This, as it stands, it's very much more difficult. Find the integer values of x that satisfy this equation. A very complicated looking equation which it's got a cube root and you've got two square roots, which make it really terrible. Anyway, the point is that from here, you see, if x is an integer, so 1 plus x must be a perfect square. One plus x is a square number. And then you have x itself is a cube. A cubic number. So you've got two which are next to each other. One of them is a square, and the other is a cube. Now, if you write down all the cubes, like starting from minus 27, minus 8, minus 1, these are all cubes. Right? And so on. And when you add 1 to it, it must be a square. And when you add 1 to this, you get minus 26, minus 7. When you add 1 to this, you get 1. You get 1, you get 2, you get 9, you get 28, and so on. And none of these are squares. This is not a square, but this is, and this is, that is not. So, oh no, wait a minute. This is not a square. So it's 0, 1, and 9. A square. So your solutions are, therefore, x cubed is either -1, 0, or 8. three possibilities. Therefore, x is -1, 0, or 2. So those are the three values of x which you can see here. But it's not quite clear that you have any more, you know. And the cube root of, oh, wait a minute. Now let's just check to see whether these are solutions. So if x is -1, let's put x equal to -1. Substitute. Left-hand side, right-hand side. Substitute x equals -1. The left-hand side becomes 1 minus 1 is 0. 1 plus 0 is 1. The square root of 1 is 1. So the left-hand side is 1. And when x is -1, the cube root of this is -1. So this is not a solution. Right. So although it looks as if it's a solution, it's not. But x is 0. Let's try x is 0. X is 0, the left-hand side. 1 plus 0 is 1. And 1 plus 1 is 2. So you have the square root of 2. And when x is 1, you have 1 here. They are not equal. So this is wrong also. And then when x is 8, the left-hand side is 8 plus 1 is 9. Square root of 9 is 3. And 1 plus 3 is 4. So square root of 4 is 2. And when x is 8, the cube root of... Right. So this is the only solution. Therefore, x equals 8 is the only solution. Okay. Because you have to substitute and check to see whether they are in these solutions, and it's not. You must get the left-hand side equal to the right-hand side for it to be a solution. And here you see when you substitute these numbers, it doesn't work. But when we tried to do it by saying it must be a perfect square. We only looked at this part here, and we looked at this part here. So we still need to look at the entire thing to see whether it works or not. Okay, but I don't. It's to show it's the only solution. I don't know. You can say x equals 8 is a solution, but to show its only solution, it's not that obvious. Okay. Okay. Let's get on to the next one. Oh, I give some kind of a reason here. Okay, so we tried all these things, and so 8 is the only solution. Then I say, since the left-hand side and the right-hand side increase as x increases, 8 is the only solution. So you have to think about that. You see, when you look at the graphs here, you'll see one graph. It's very difficult to draw the cubic graph. So that's why this is not a straightforward problem. You get the square root graph goes like this, and the cube root graph goes a little steeper, like that. So these two graphs only meet at exactly one spot, and therefore that is the only place where both of them are equal. Right. Um, but that's a loose way of saying it, and it's too advanced for junior students. But you can be quite happy with saying that X is the only solution. 8 is the only solution. Okay, now let's just get on to the next problem. We're in question 7 now. We go to question 8. Question 8, it involves prime numbers.